Hello and welcome to Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over at the University of Helsinki. I study the universe. So I'm a cosmologist, which means I study the universe, the contents of the universe, how everything evolves, how everything interacts, basically everything happening inside the universe. Hey Anjin, first, great to see you. As always, thank you for stopping by. So yeah, I study all of the cool things happening inside the universe. I've worked a lot on dark matter in the past. Currently I'm working on gravitational waves, really fun topics. There's a lot of things about the universe that I'm completely fascinated about. And I love jumping here on HAPS or wherever you're watching me from and talking about all of the cool things happening inside the universe. So if you're joining me from HAPS, if you're joining me from Twitter, from Twitch, from YouTube, from Reddit maybe, welcome wherever you're watching from. It's great to have you here. So yeah, I like coming here and chatting about the universe and answering any questions you people have. So this is an interactive stream. The idea here is that you can ask me anything you want. Hey David, great to see you. Thank you for joining. I'm not sure if you've got a notification by now. Hopefully they fixed that. If not, no, you know when to find me. I'm always here at the same time. Hey Paul, nice to see you as well. So yeah, I like talking about the universe. Still buggy? Oh, sorry to hear that. Hey Scott, thank you for being here. Got some of my regulars coming in already. Always nice to see you every Sunday on the spot coming in here to catch me chatting about the universe. So yeah, I like chatting about all of the cool stuff happening inside the universe. Still no notifications? It's like a month now with no notifications. You'd think they would have fixed this by now. I will report it again, see if we can get an update for when the notifications are going to be fixed. And hopefully they will be fixed at some point soon. But if not, follow me on YouTube. The YouTube channel is Cosmology, and there you can be guaranteed to always get the notifications. I think the YouTube one is about 30 seconds delayed, but you should still get the notifications there. So if in doubt, follow me over on YouTube as well. So I do actually have a topic to talk about today because there was a big announcement this week. Right, yes, and before I start, thank you for reminding me, Scott. So I have mentioned several times that there is one Easter egg hidden in the Cosmology logo. And after last week's show, 2 people messaged me with the answer to the Easter egg. So both Scott and David Dunn have now found the Easter egg in the Cosmology logo. So big congratulations to Scott and David for finding that. This just goes to prove there is an Easter egg in the logo and it can be found. Last week I dropped a huge clue and it allowed some people to actually find the Easter egg. So well done, Scott, you did find the Easter egg, as did David Dunn. So we now have 2 people who have found the Easter egg in the Cosmology logo. But please do keep your guesses coming because we're not going to reveal this publicly, at least not for some time. So everyone can still try to find the Easter egg in the logo. And thank you for reminding me about that, Scott. So yeah, there was something cool happened this week in science, and you might have already seen this on the news because there were a lot of science media articles, popular news articles about how how particle physics might be completely broken and how we might be in a whole new era of particle physics. Very sensational headlines like particle physics broken, scientists baffled, usual stuff. And as always, this is a bit sensationalized, it's a bit exaggerated. There was a very cool announcement this week, but as always, I would like to err on the side of caution and remind everybody that sometimes newspapers and news agencies do have a tendency to overhype some scientific discoveries or scientific announcements, which isn't necessary in my opinion because the science is already cool enough that it doesn't need the overhype. So let me just get this right at the beginning. We have not broken physics. We have a new interesting result. It does not mean we need to check out everything we know about physics yet. So before I get to the announcement, I want to set the scene a bit and talk about what we know about the standard model of particle physics. So usually I'm talking about dark matter and dark energy. So let's just recap here. The universe has 3 main components. Everything you see, everything you're accustomed to, everything from the stars you see at the night sky to me, to my table, to my coffee mug, all of this is normal matter. And normal matter only accounts for 5% of the energy budget of the observable universe. Then there's 26% in the form of dark matter. So dark matter is this weird type of matter that interacts via the gravitational force, but doesn't interact via the electromagnetic force. This means it doesn't emit light, it doesn't reflect light, it doesn't absorb light. Light and dark matter just don't really talk to each other. But dark matter does interact via the gravitational force, and this is how we know it's there in the universe. Dark matter accounts for 26% of the observable universe. The remaining 69% is in the form of dark energy. So dark energy is this real type of energy that is driving the accelerated expansion of the universe. It is pushing everything away from everything else. And that's basically everything we know about dark energy. So 95% of the universe is either dark matter or dark energy. And usually, when I'm talking about cosmology, those are the things I focus on. Start 60-minute clock now. Okay, let's see, maybe. Depends how long I chat for, but great to see you, James. Thank you for joining, as always. I'm not sure if we have the Reddit connection today. If someone on Reddit wants to confirm if we do have a Reddit connection, that would be nice. I know that's also slightly buggy. So yeah, normally I talk about these two big components, these two dark mysterious components of the universe. But today I'm going to focus on normal matter. So I'm going to focus on the 5% that we actually know, that we understand. So everything we can kind of interact with, things we can touch, things we can see. So I'm going to be talking about normal matter today. And in order to talk about normal matter, the way we do this is with the standard model of particle physics. So the standard model of particle physics can be seen in different ways, but it's basically the mathematical description of all of the observed, all of the particles and all of the structures in the universe we can see. So the standard model of particle physics gives us a description of the normal matter in the universe. It doesn't include dark matter, it doesn't include dark energy, it doesn't include gravity, I'll come to that later, but it does give a description of the main particles that we know of in the universe that we can see and how these particles talk to each other. So it really does provide not only the building blocks for normal matter, but also the rules that these building blocks have to obey. So it's kind of if you're giving a Lego set and a set of rules like these pieces fit together in this specific way. This is what the standard model of particle physics does for us. Today I'm catering to the 5% indeed. Today I'm going to be classist and focus only on the 5% and not the 95% of the rest. But anyway, let's get into the standard model of particle physics, and as always, if anything I say is not clear, please do ask questions, because this is how we learn things. If you ask questions, then I realise that I need to explain things in a different way. So please do ask questions if you have any questions, and I think you can come up with, just feel free to ask. This is the point of the stream, else it's just me monologuing, which is also fun, and then I feel like a supervillain. If I start talking about overthrowing the government and, plotting my world dominion, it just means I've gone full supervillain, and at that point I'm monologuing too much. Okay, so we're going to build up the standard model of particle physics. I'm going to talk through everything quite slowly today, just to make sure we're all on the same page with the standard model of particle physics. So what you can see up above or over to the side, depending on the platform you're watching on, is the cartoon representation of the standard model of particle physics. Now this is divided first of all into two main families. What's the fundamental difference between mesons and leptons? Great question, Scott, so let me get to that in one sec. So this here is divided into two main groups, first of all. On the one hand, we have fermions. Now fermions are the ones you can see here in purple and in green. And fermions are ones that build up the constituents of matter. So fermions are ones that can actually go together and do things. Then we have the bosons. And the bosons are the ones that tell the other particles how they can talk to each other and how they can talk to themselves. So the bosons are the ones that gives the laws of physics, while the fermions are the ones that can be put together to form other things. Now, one big difference, when Deanna starts creating a team of dark matter enhanced super soldiers, we should worry. Yeah. The good thing about having an army made of dark matter is nobody would see them coming. The bad thing about having an army of dark matter is they wouldn't really be able to do much. So, yeah, I'm much more likely to train an army of ravens than an army of dark matter. But yes, if you start seeing me amassing an army of dark matter, something might be up there. At that point, maybe stop me from monologuing. Okay, so we have the fermions and the bosons. And the key difference between fermions and bosons at the quantum level is that fermions have to obey the Fermi exclusion principle. This means that fermions cannot be placed overlapping. They cannot occupy the same space. There always needs to be some distance between fermions. You can't overlap them. Whereas bosons can actually occupy the same space, so to speak. So they follow slightly different rules. We have the fermions and the bosons. Now within the fermions, there are two main families. There are the quarks and there are the leptons. The quarks are the ones that give structure to other things, and The cool thing about quarks is they can never be found alone in the universe. You can't just find one quark. You always find either 2 quarks or 3 quarks together, bound together. You can also potentially find tetraquarks, so that's 4 quarks, or pentaquarks, which is 5. You can find these configurations, but a quark can never be found alone. You can't just say, like, hey, look, I've got a quark. The leptons, on the other hand, can be found alone. My army could be called the Communist Manifesto Brigade. Let's not get into communism today, shall we? Because then we'll be here all night. So we have the quarks, we have the leptons. CMB for short. Now I like you, Scots. My army will be called the CMB army, of course. So yeah, we have the quarks, we have the leptons, we have the bosons. Now again, the quarks and leptons are just types of fermions. Now all of this is what you can see in the image above or to the side. So I'm just walking you through what you can see here in the image. Now, as we started figuring out what the universe was made of, what normal matter was made of, we first found 4 main components, 4 main particles that we could play about with, so to speak. The first, hey Do, great to see you. Thank you so much for the Heart Thumb Award. I do really appreciate it, and nice to still see you on Haps. I know you're shifting over to Twitch. It's nice to see you on Haps again. So when we started figuring out what atoms are made of, when you break down atoms, you find a nucleus. And if you break down the nucleus, so a nucleus is made up of protons and neutrons. And if you break down the protons and neutrons, what you're going to find is a combination of up quarks and down quarks. So you have up quarks, you have down quarks. And you put a couple of up quarks and down quarks together, you get protons or neutrons. So a proton has 2 up quarks and 1 down quark. A neutron has 2 down quarks, 1 up quark. As I said before, these cannot be separated. These quarks always need to exist with other quarks. Then, if you put protons and neutrons together, you form the nucleus of an atom. But going around this nucleus, not technically going around, kind of in a phasey cloud, you have electrons. Are all these items in the Standard Model observable in the Hadron Collider, or are we talking about a crazy layer of size? That is an excellent question, and I will get to this. I promise I will get to this. So there's also the one that I need to answer from just now as well about mesons. I will get to that as well, I promise. But if not, please do ask me again. So we have the up quark, the down quark, and the electrons. These are the 3 we need to make all atoms. Now everything in the universe, from me, my table, to a mountain, to a star you see, let's not go to stars. Everything you see here on Earth is made up of a combination of up, down, and electrons. These 3 particles is what makes just different configurations of these 3 particles. Hey David Dunn, great to see you. Thank you for joining as always, and thanks for testing the Twitch link. So everything in the universe is just a different configuration of up, down, electron, everything on Earth that you can see. But also we figured out there was a 4th particle, which is called the electron neutrino. Now the neutrinos are slightly different to the other ones in the sense that neutrinos travel almost at the speed of light. They're really, really, really fast. And they don't really behave the same way as the other ones. They just travel around, they do their own thing, and I'll get to why they're slightly different in a minute. But hey, thank you for the Love Burst Award, David. I do really appreciate all of the awards. Once we found these 4 particles, the up-down electron and the neutrino electron, this was the first idea that we had of these are the building blocks. But then we found that there is actually 3 families of these particles. So all of these particles that I'm describing are the first column that you see here in the Standard Model. So the up, down, electron, and neutrino. It always bugs me that quarks are considered fundamental particles when they can't exist by themselves. But you cannot break a quark down. So a quark of developing a cough, this is not good, just losing my voice. So a fundamental particle is always the smallest building block that you can have. And as you say, we cannot find the quark by itself. But we do know that quark is the smallest element we've been able to find. So you can't really call a proton a fundamental particle because it is made up of quarks, of ups and downs. You can break something down into a quark, that is true. Yeah, let's not go on to the cucumber tea. I do actually have tea with me. It is not cucumber, it is raspberry, which is much more reasonable flavour to put in tea than the weird cucumber tea I was drinking last week. So we have this first family, up, down, electron, and neutrino. And what we actually found is that we have 3 copies of these families. So we have 3 generations. So for the up particle, we also have a heavier one that is called the charm, and an even heavier one, which is the top. For the down, we have a heavier one, which is called the strange, and an even heavier one, which we call the bottom. So then we have the 6 quarks, up, charm, top, down, strange, bottom. For the electron, there are also three families. There's the electron, the muon, and the tau. And for the neutrinos, there are also three families. There's the electron neutrino, the muon neutrino, the tau neutrino. So from a mathematical perspective, when we write out the standard model, we can explain why we have four different types of particles, why we have up, down, electron, and electron neutrino. What we cannot explain is why we have three families. Why not 10 families? Why not 4? Why not 2? Why do we have 3 families? This is something we cannot explain. But together, these 12 building blocks give us all of the fermions. So again, we have 6 quarks, up, down, charm, strange, top, bottom. They're ordered here in the chart from mass, lower mass on the left, higher mass on the right. And then we have the electron, muon, and tau. And we have the 3 neutrinos, which are the electron neutrino, the muon neutrino, and the tau neutrino. What happened to beauty and truth? They taught us those in high school. Did they change their names? Yes, they did. So the top and bottom used to be called beauty and truth. And in some textbooks, you'll still find that they're called beauty and truth. But at some point, the name just changed. I honestly don't know why the name changed. But at some point, they just became the top and the bottom. I think from the start, there were the 2 competing names, and just top and bottom became more usual, more widespread, the more common name. But yeah, we did used to have, if you've heard of beauty and truth, they're the top and bottom quarks. Quarks in protons, neutrons are in 3s, and there are 3 families. Is that a coincidence? Yes. Yes, it is a coincidence. So there was a question before about the difference between mesons, leptons, and all of these things. So when you have 3 quarks together, what we call this is a baryon. But you can also have 2 quarks together, like for an example, an up and an down, just 2 quarks together, an up and a down, for an example. And this is what we would call a meson. So if you've heard of baryons before, this is just saying protons and neutrons, and basically anything formed of 3 quarks. If you hear the word meson, this means something formed of 2 quarks. So this is a great question here, David, but we can actually have things formed of 2 quarks, so it's a complete coincidence that we have 3 families and 3 quarks in protons, because you can also have things formed of 2 quarks. 2 quarks, if you have 2 quarks, you have a meson. If you have 3 quarks, you have a baryon. If you have 4 quarks, we give it the very useful name of tetraquark, tetra being 4, quark. If you have 5, we have pentaquarks. These have all been found. Then if we have 6, this would be a hexaquark. We're not completely sure if this exists. There are some interesting ideas behind hexaquarks, but we're not yet sure if these exist. They have not been found yet, at least. Okay, so I think that answers the question. Let me just go back. What's the fundamental difference between mesons and leptons? I hope that question is now answered. Leptons are just the family that includes electrons and neutrinos, while the quarks themselves can either be found as mesons or as baryons. Then there was another question. All these items on the standard model observable in the Hadron Collider. We'll get back to that one later. Yes, definitely. Yeah, okay, so I think that answers those questions for now. So, recap, we have quarks, we have leptons, together these make up the fermions. These are the ones that are the building blocks. We know why there are 4 of these, why there's up, down, electron, neutrino. We don't completely know why there's 3 families, but there are 3 families, each family heavier than the previous one. Now here's the cool thing. These families are very difficult to find something in the second family or the third family, so the second column or the third column, because these particles have a tendency to decay into the smallest unit of their family. So if you have a top, it might decay into several ups and downs. If you have a bottom, it can decay and eventually produce a down quark. Taus decay into muons, muons decay into electrons. So it's much more common to find particles in their first family than in their higher iterations. So this is pretty cool, because this is why it's very common to find up quarks and down quarks, but finding charms and strange and tops and bottoms is a bit harder, because they are short-lived. Seem to recall that they have charges in thirds, so also a 3ness, yes. And this is so they do have, I'm not sure how much you can read the small print here on the image, but there is the mass of each particle, which is the top number in the left-hand corner of each subplot. There is a charge and there is a spin. And as you're just saying here, for an example, the charge of the up is 2/3. The charge of the down is minus 1/3. If you take 2 ups and 1 down, you get a positive charge. This is why you have the proton. If you take 2 downs and 1 up, you have neutral charge in the neutron. But yeah, their charge is 2/3 or minus 1/3, depending if you're the first type or the second type. This is true. But yes, it's plus 2/3 minus 1/3. Could change the units and multiply everything by 3. We could do that, but then you'd have to say like the electron has a charge of 3, which doesn't make sense, especially because the charge is usually referred to as like units of the electron charge. So the electron charge is taken as the unit, and then everything else is products of that. Hope that helps. But yeah, don't worry if this is confusing. It is a very complicated model. I'm trying to break it down into its simple parts, but it is a complicated model, and the way it comes together is extremely complex. Okay, so we have these families, we have these different particles. We always decay from the heavier ones to the lighter ones if possible. So what tells these particles how to decay or how to talk to each other, or why does it matter if they have a specific charge? And for this we need to bring in the forces. So there are 4 forces that govern our universe, 4 forces of nature. The one that we're most familiar with, that we deal with on a day-to-day basis, is the gravitational force. We know what gravity does. It keeps us in orbit around the sun. If I drop a pencil, it's going to fall down. If I throw an apple at someone, it's going to hit them. Or if I'm probably going to miss, it's going to fall close to them at least. So all of these things are controlled by gravity. Is neutrino mass taken at rest? As I understand, mass increases with speed and they're fast. Yes, all of the masses here in the particle, in the standard model, all of the masses you see listed here are the rest mass, the internal mass of the system. Once the particle gets accelerated, then it has another mass that comes from its, kind of another energy term that comes from its movement. All of this is its rest mass. Neutrons by themselves are unstable, but with the quark interactions with the protons, it becomes stable. Yes, exactly. I will get to that when I get to the forces. So the first force, the one that we're used to, is gravity. Gravity keeps us in orbit around the planet. Gravity tells us why objects fall down. Gravity tells me not to jump out with a window. I can, I shouldn't. This is gravity. This is the force that we are accustomed to. And we have a theory to explain gravity, and this is general relativity. General relativity is Einstein's theory, and it tells us basically how to understand gravity. Now, the problem with gravity and with general relativity is that it is what we call a classical theory. It explains large objects. It explains things that we can see, like planets, big things, us. We're not quantum systems. And it's very, very difficult to match a classical theory into the quantum world. This is why gravity is not part of the standard model of particle physics. We have no idea how to put gravity into this picture that you see here. In order to put gravity together into this, we would need a theory of quantum gravity. This is something that a lot of people are upset about with the standard model, because why is gravity not included? We don't know how to include it. So, even though gravity is the force that we understand the most, gravity is not invited to today's discussion because we're talking about the standard model. So, we can kind of eliminate gravity and we focus on the other 3 forces. Now, of the other 3 forces, what does rest mass mean in rest mass? At rest relative to something, or is there an absolute standard of rest? Great question. So, it's basically the mass that could be converted into energy if you do no other. How do you explain rest mass? This is a great question, David, and it's stumping me because it's one of those things that intuitively I know, but explaining it is always difficult. So yeah, if you take the particle at absolute rest, I know it's always difficult because there's always relative motion, but if you take a particle at absolute rest, it has a relative mass, and kind of rest mass, and this is the mass that we give here. So of course, if a particle is moving, when you measure its energy, it's going to have a slightly different mass. So you'll notice that all of the masses here are given in terms of GeV over c squared, so they're given like energy c squared. And if you remember Einstein's formula of E equals mc squared, this is basically mass if we take the energy divided by c squared. So this is the at-rest energy of a particle, we divide it by c squared, we get the rest mass of the particle. So that is why it's given in terms of GeV over c squared, because then you can directly see its energy over c squared, which is E equals mc squared. Opinion question, but what do you think? Newton would be upset with Einstein because he improved his theory, or happy that it got figured out better? I like to think that science is a collaborative effort. Everything we put forward, we know is going to be, we hope is going to just be reused in the future. If someone 10 years from now or 5 years from now proves all of my work wrong, great, this is how science progresses. Now, I can't speak for Newton, but I don't know what Newton did, or what Newton thought. But in general, science is a progressive effort, it's a collaborative effort. And sometimes you come up with something that is just a step forward. Now, Newton's gravity is excellent. It's a very, very good description of exactly what it tried to describe. And if you're talking about the motion of stars in the sky, you're more likely to use Newtonian gravity than Einstein's relativity. Some people have big egos, that is very true, especially in physics and especially with cis white men. But anyway, that's a whole other rant for a whole other day. But yes, some people have very big egos in physics and in general. So I can't speak for Newton, but in general, Einstein did not really prove Newton wrong, he just extended the validity of Newton's theory. So I think they're both useful for different things, and they both work well together. So I don't think there should be any hurt feelings between Newton and Einstein. Okay, so we're going to move on to the other three forces that we can put into this picture here. Now, the first force I want to talk about is one that we're all used to, which is the electromagnetic force. So, and I just realized I made a comment but didn't completely answer it, so I'll get back to that later. Anyway, so the next force that we're all accustomed to is electromagnetic force, electricity and magnetism. This is what gives atoms their chemical properties. It's what generates magnetic fields. It's what generates electric fields. And we've harnessed this for most of our technology. Anything that uses electricity is based on the electromagnetic force. Now, the electromagnetic force affects anything that has charge, which you can see here is everything on this table. Everything on this table has charge with the exception of the neutrinos. So we saw before that, the ups and the downs have spin 2/3 and minus 1/3. The electron has charge -1, and then the neutrinos have no charge. So any type of electromagnetic interaction is carried by the photons. So the photons are the first boson we're going to see today, and the photons are the ones that carry the electromagnetic force. So anytime we have an electric interaction or a magnetic interaction and an electromagnetic interaction, you can kind of imagine the two particles throwing a photon back and forth between themselves. This is what produces the electromagnetic force. So the photons carry the electromagnetic force. The photons are here in the picture. We know how photons behave. We know that anything with charge can interact with the photon. All quarks can interact with photons. Electron, muon, tau can interact with photons, but the neutrinos do not interact with photons. Everything can be magnetic if you try hard enough. Well, it depends what you're doing with things. This is definitely a much better tea than last week. Also, tea's a bit cold because I ignored it for half an hour. Okay, so we have the photon. And I do promise I'm building up to a core result. I'm just reviewing everything we know about the standard model because this is what we need to understand the core result. Okay, the next force I want to talk about is the strong force. The strong force, as the name implies, because we're so good at naming things, the strong force is the strongest force we know of. And the strong force is the one that's responsible for quarks not being able to be found alone. Now, the big difference here is that if you think of the electromagnetic force, if you have an electron, it's going to create an electromagnetic field around it that goes out in a circle. Whereas the strong force doesn't radiate out in a circle. It kind of creates a tube between one particle that connects to another particle. And this is why quarks cannot be found alone, because the strong force pulls them together. In the case of a proton, for example, you have two ups, one down. So you can imagine three particles and connected together in the middle with the strong force. And the strong force is so strong that if you try to pull apart two quarks, the amount of energy you need to pull apart these quarks is actually enough to create another pair of quarks. So if you have two quarks and you really try to pull them apart, what you're actually going to end up with is 4 quarks, 2 here and 2 here. This is why it's called the strong force, because you just cannot overcome this force. It's really difficult. And this is why you can't find quarks by themselves. So this is back to the discussion before of should quarks be called fundamental when you can't actually separate them. We know that these are the fundamental constituents, and while I can't pick it up and say, look, here's a quark, I can say this thing here is made of 3 quarks. So we know that protons and neutrons and all of these things can be broken down to quarks, and you can have different configurations of quarks which lead to different particles and different properties. So in their essence, they are really the fundamental building block, but we just can't find this building block alone because the strong force holds everything together. Now the strong force glues things together, so the particle that carries the strong force is called the gluon. We are so good with names. So the gluon is the one that glues everything together. Okay, We've seen two of the forces, two of the bosons, photon and gluon. And obviously we're ignoring gravity because we don't know what to do with gravity. And then we have the final force. We have the weak force, because if we have a strong force, we need a weak force, because good at naming things, this is a recurring theme. The weak force. The weak force is the one that is responsible for everything decaying to its lowest mass. I mentioned before that we usually find things in the first generation. We don't find so many charms, we don't find so many tops, because these are unstable and they always decay. And this decay, what makes a tau particle, for example, decay into a muon and a neutrino, is the weak force. What makes the muon decay into an electron and a neutrino is the weak force. So the weak force is responsible for radioactive decay and in general for the decay of particles. Which of these forces keeps electrons revolving around protons and neutrons? This should be the electromagnetic force, because this is the one that is responsible for mediating the positive attraction of a proton with the negative attraction of the electron, or the negative charge of the electron, the positive charge of the proton. What would tachyons do, hypothetically? You know, I love tachyons. So tachyons are not part of the standard model. Tachyons are a hypothetical particle that would have negative mass and would travel backwards in time. And this makes no sense. So this is something that mathematically you can pull out with your equation and say, look, you know, if I solve these equations in a specific way, then I can find this particle, but that doesn't mean that it's a real physical solution. So it's just very hard for us to think about a particle that will travel backwards in time and have negative mass. This isn't something that makes any sense physically, but it is something that mathematically can exist. So it is a hypothetical solution, but it is not the it is not a particle that we believe exists. Do weak forces make things decay, or do weak forces result from the decay? That is an excellent question. That is a really good question, yeah. And I think it's very much depends on what you define directly as the force. Now we know that the force is carried away by a boson. So if you have a tau, for an example, this tau can decay into a muon and into one of the bosons of the weak force. So here you already have the weak force because of the particle. So is it the weak force that is causing the decay? I would say yes. The weak force causes the decay, this produces the boson. So yes, but that is an excellent question, and it's definitely one to think about. But the weak force is responsible for things decaying, it's responsible for us only seeing this lower family, and it is also one of the reasons we can actually see things we can actually see stars, because of the weak interactions making things decay. You produce a lot of photons. These photons obviously carry away the light. So a lot of the processes in the sun, and another way of thinking about it, I should have mentioned this before. Thank you for the love burst award, David. So I forgot to mention this before, but the strong force is responsible for nuclear fission. So anytime you split an atom and you would release a huge amount of energy that has been obviously misused, this is what we get, this fission thing of splitting things, is because of the strong force. You are splitting something, the strong force is the one that is bringing out the energy here. Then the weak force is the one that is responsible in the other direction. Sorry, other way round. Fusion has a strong force because you fuse things together with the strong force, and when you split something, you're producing radioactive decay. This is fission. Yes. Is that correct? Yes. I always mix up fusion and fission, and I need to think about how they come together. But yes, the strong force can be related to fusion, the weak force can be related to fission. So that is something else that we can thank the forces for. Maybe I should stop thinking cause and effect in quantum. Yes, please stop thinking cause and effect in quantum. It makes everything a bit messy and difficult, but they're great questions, but these are difficult questions to answer. Okay, you think you're misunderstanding the gluon. How is it different to strong force other than magnitude? So the gluon is really just the particle that carries the strong force. Basically, when you have three quarks together, these quarks are actually swimming in a bath of gluons. So the gluons are the ones that are holding everything together. They're the glue that's binding the quarks, and they are the ones responsible for the strong interaction. Why is the strong interaction orders of magnitude stronger than the weak interaction? Good question that I do not have the answer to. It's just a much stronger force, and this is something that we can pull out with, or that we encode into our standard model of particle physics. So it is just a strong force, and I'm realizing there's so much I should have reviewed before coming into this stream. It's like, I remember my standard model, and now your questions will make me think, oh god, there's so much I should have reviewed before doing this stream today. But, you know, we're on a journey of learning here together, and I'm making a mental list of all the things I should check. I should have just brought a particle physicist with me today. That would have been easier. Okay, now the bosons that carry the weak force, which is the one that causes everything to decay. Yeah, one is called strong, one is called weak. That's why one is strong and one is weak. Exactly, let's go with that. Thank you, David. Now, the weak force is so called that it actually has two bosons, or actually three bosons. So the weak force can be carried away by a W+, a W-, or a Z boson. So we actually have three here. We have the W bosons and the Z bosons, or the Z bosons. And this completes the next level of our standard model of particle physics. So again, we have the fermions, which are made up of quarks and leptons, which are the building blocks of the universe. We have the bosons, which carry the forces. The gluon carries a strong force, which binds everything together. The photon carries the electromagnetic force, which causes electricity and magnetism. The weak force is the one that's responsible for radioactive decay. It's the one that causes everything to decay into its lowest family. And it has three bosons, the Z boson and the W+ and minus bosons. Okay, and as I said before, we have no idea how to put gravity into this picture. When all three W and Z bosons cooperate, they're still weak? Yes, they're still weak. They're still orders of magnitude weaker than the strong force. So this completes the forces. So by now we have all of the building blocks and how these building blocks can talk to each other. As I mentioned before, we don't know why gravity isn't here. We don't know how to put gravity into this picture. And then there was one piece missing here. There was one piece of the standard model which makes the picture more complete. And this is the Higgs boson. So everything I mentioned up till now, all of these particles, initially should not have mass. The only reason that anything in the universe has mass is because of the Higgs boson. So the Higgs boson is a field. It's a boson, it's a field. It just means it's everywhere in space-time. It permeates the universe. There's not really a good analogy for the Higgs boson, but one that I like to use is to imagine that the Higgs boson is like treacle or molasses. It's something that adds a bit of difficulty moving. So it makes things slow down. It kind of gives objects mass by creating this thing that they need to interact with. And it's a bad analogy because you should not think of the Higgs boson as the treacle or molasses of the universe, but it is an analogy that it's something that slows everything down. I'm fine with not having a boson for gravity since it's just space-time curving anyway. Yes, there could be a boson potentially called a graviton, which would explain gravity is carried away in gravitational waves. We still don't exactly know how to put a potential graviton here. So if I really want to lose mass, I should get rid of the Higgs boson. Potentially, but if you get rid of the Higgs boson, you would trigger a vacuum decay and wipe out the entire universe. So please don't get rid of the Higgs boson anytime soon. But yes, the reason you have mass is because you're made up of particles that spoke to the Higgs field, which gave them mass. Anything that interacts with the Higgs field gets mass. You might see here that gluons and photons do not have masses. Everything else does have mass. So everything except photons and gluons are talking to the Higgs field, which means they all have mass. I'm glad to hear you're mind blown by this, James. I really hope this is clear. If not, please do ask questions. Because what I've just given is a 30-minute summary of one of the most elegant and well-tested and most thorough models we have in particle physics, and indeed in science in general. The amount of predictions we've got from the standard model, the amount of things we've done with the standard model is incredible. So this is our picture. We can put it together in building blocks like you see above with the different generations, the different families. We can also describe this mathematically. And you can write out the full mathematical equation describing everything I talked about, describing the Higgs boson, how the Higgs interacts with everything, how the strong force works, how the weak force works, how the electromagnetic force works, how it behaves with all of these particles. You can put this together in some mathematical equation. There are different forms of it. You can write the most condensed form in 4 lines, which fits on a coffee mug, or you can stretch it out to 1 page if you want to derive every single term. But this is everything that makes up the visible part of the universe is encoded in this picture. There are problems with this picture. We don't know how to put gravity in there. This picture, of course, does not explain anything about dark matter, but also that was not its intention. It does not explain why we have three families and why the top is, for an example, so many times bigger than the up. We don't know why they have these relative masses. We don't know how the neutrinos kind of behave properly. There's a lot of things that this doesn't tell us, but it is one of the most well-tested models that we have. There's also cool things like the mass. So I mentioned here that everything has mass, including the Z bosons and the W bosons. So the weak force bosons have mass. And once you've got a measurement of the W boson mass, you can use that to predict other particle masses. So before we first actually measured the top quark, we were able to predict its mass based on having measured the W boson. And before I get into this too much, there was a question a long time ago, early on in the stream, of which of these particles can we see in a collider? And I want to come back to this now. So I mentioned before that things like to decay into into the first family. So what you usually actually do at a particle collider is you smash together protons and antiprotons. Because the idea here is that if you smash together these quarks at high enough energies, you will create a cascade of other particles coming out. You might create muons, for an example, but these muons are going to decay very quickly into an electron and neutrino. But you can trace the muon before it then decays into something else. You might decay into photons, you might decay into smaller bosons, into smaller quarks. But you will have these chain of decays, these kind of smashing of particles together that creates these jets, and this is what you track. So in a collider, like the Large Hadron Collider in Switzerland, it's very difficult to point and say, look, here's a specific particle. What you can do is you can follow the path that these particles are taking. For an example, if you see an electron and an electron neutrino going off in different directions with specific energies, then you can trace it back and say, okay, these were produced by a muon and a W boson, potentially, that had a specific mass. So then you can reconstruct what happens. So there are some things that are easy to find, like electrons we know how to find. Muons, we can see these in our detectors before they go off and do some decay as well. So there are some things we can track, and there are some things we can't track. Like neutrinos are very difficult to see in a detector, but you can try to map them by the energy that is carried off. Higgs boson as well, you don't directly see Higgs. What you see is decays, which you then reconstruct as the only thing that could have produced this is a Higgs boson. So I hope that answers the question. Not all of this is visible directly in a collider, but we can reconstruct the pieces, especially when we have this mathematical equation that tells us how all of the pieces fit together. So we'd measured the W boson by doing this reconstruction thing multiple times. And with the measurement of the W boson, we were able to predict the mass of the top quark. A few years after the prediction, we actually measured the top quark with the expected mass. This was a win for the standard model. And then you can go one step further. Once you have the top mass and you have the W boson mass, you can predict the mass of the Higgs boson. So while these are not things that you can mathematically pull out, once you measure a few things, because everything is connected, you can predict other things. So back in the early 2000s, there were predictions already for the Higgs boson mass based on the measurement of the top and of the W boson. And then in 2012, there was the famous announcement of finding the Higgs boson at the Large Hadron Collider with exactly the predicted mass. This again was a win for the standard model of particle physics. So the standard model of particle physics does a lot for us. It's very well tested. But we know it's not perfect. We know that there are things missing. We want to find what is beyond the standard model because we know there need to be things beyond the standard model because this is not enough. This picture is really not enough. We know there needs to be more. So if you want to look beyond the standard model, the place to look is anywhere where there's a slight crack. Anywhere where your prediction and your measured values start to pull apart slightly, these are the cracks that you need to explore because these might provide the window to beyond the standard model physics. About a year ago, I had somebody on my stream talking about the G-2 anomaly, which is when you measure the specific magnetic moment of the muon. There's this tiny, tiny discrepancy. So this is a crack where you can start to hammer a wedge and see if you can break the standard model. Okay, 45 minutes into today's episode, we get to the point I'm trying to make. That was a long-winded point. Now, I mentioned before that you can use the mass of the W boson to make other predictions, but you can also go the other way. Knowing what we've measured for the top mass, for the Higgs boson mass, you can make a theoretical prediction for the W boson mass. With everything else, other quantities that we've measured, you plug them into the standard model of particle physics, you measure, or you get a prediction for the W boson mass. Now, as always, if you can make a prediction, you want to measure this experimentally. Crack is the Fisher like fission. Thank you. That is not going to help me remember because I have like 10 different ways of remembering fission and fusion, and every time I need to bring these two words up, my brain just crosses all of my knowledge about these two words. I'll add it to the like hundreds of ways I can remember it. It will not help. But thank you, Scott. So it's just two of those things that my brain doesn't want to separate. It's like green and yellow. My brain cannot tell those two apart. Anyway, back to the topic here. If we can make a prediction for the W boson mass, this is something we can test. We could design experiments that will measure the W boson mass. We compare it to our theory. If the standard model is perfect and complete, these two measurements should agree. Up until now, we thought they did. Up until this week, our predictions from the standard model matched our observations for the W boson mass. On Thursday this week, there was an announcement by the CDF team. So the CDF team, let me get this name correct because I always mess up the name. Where is the name? The CDF is the collision detector at Fermilab, and they were working on data from the Tevatron experiments. So Tevatron is a particle collider that was operating, let me get my dates correct, it was operating between 2002 and 2011. During this time, it was crashing together protons and antiprotons. And at this point, W bosons often appear. When you crash together enough protons and antiprotons, you can produce W bosons. So at the Tevatron, they got over 4 million W bosons produced in this time period between 2002 and 2011. 4 million W bosons produced. The CDF team have spent 10 years using this to measure the mass of the boson, of the W boson, with the idea to get the most precise measurement ever of the W boson mass. They released their results this week on Thursday with a new paper, after 10 years of scrutiny and trying to improve their result as much as possible. And what they found is that their result is a bit different than the prediction. A bit different. What do we mean by a bit different? It's off by 0.1%. Now, 0.1% might not seem dramatic. It's very small. If you're off by 0.1%, you're not close enough. But the level of precision that they've achieved with their measurements means that this 0.1% is statistically 7 sigma away from the standard model value. What does 7 sigma mean? It means that if the standard model value is the correct value, the chance of getting this measurement by fluke, by accident, is 1 in 800 billion. So there is a 1 in 800 billion chance that this is a statistical fluke. This does not mean that we have detected the standard model to be broken at 7 sigma. It just means that one test where we have a prediction and we have an observation no longer match. And I want to bring up the figure from the paper, one of the main figures, and it's a scary figure. There's a lot of stuff in it, so we're going to walk through it quite slowly. Let me just present this one on screen here. So what you can see here is one of the results released by the CDF team on Thursday. And of course, HAPS has cut off the plot. It's really annoying. Okay, I need to adjust every image to fit the resolution on HAPS, which is pretty annoying because this plot is now cut off. But let's walk through the plot anyway. I'm going to try something else because this is going to annoy me because I need to actually see the axis here and it's cut off. Okay, I'm just going to try to bring up the figure in a different way here to try to fix this slight issue that I have right now. So let me just try and screen share instead of presenting on screen. Just bear with me a minute while I try to bring up the image properly because I didn't account for the fact that it might be cut off. Okay, so the one we want is this one here. And let's see how much we can get away with doing this. Okay, I think now it's not as pretty, it's a bit small. Let's see if I can make it bigger. Okay, so hopefully now you can see the image in all its glory and you can actually see the axis. And I know there's a band here saying all figures, but that's fine. We can live with that. Okay, so what you see on the vertical axis here is the mass of the W boson. What you see on the horizontal axis is the mass of the top. Now these are things that we can put together. You can see the purple band going across the center. The purple band going across the center is the prediction we have from the standard model of particle physics. Now, in the dotted line that you can see going around in the circle, this was the last experimental result using Tevatron data. That or the last result using, not the most recent result, the last result by the same collaboration. And you can see that it was very slightly higher, so the mass of the top does not change, but the mass of the W particle was very slightly higher than the standard model prediction. The new result that they released very recently on Thursday is the red one, and the red one you can see is substantially higher than the purple one. And this substantially higher is important. So let me just stop sharing and go back to the comments because I forgot to acknowledge the comments there. You switch to YouTube when I show graphics, yeah, that's good because on HAPS it was super reduced. I hope you were able to see the image in the end. So on Thursday there was this announcement that the most precise measurement ever of the W boson mass is 7 sigma away from the standard model value. What does this mean? It means there's a crack in the standard model. There's something that we do not understand. There's a prediction and an observation that are slightly off. This is interesting, this is exciting, because what could cause the W boson to have more mass? What it could be is another particle that we haven't seen that is bumping into the W boson and affecting its mass very slightly. Does this mean we have found new physics? No. Does it mean we need to chuck out the standard model and start again? No. Now, there were a lot of headlines of physics broken, scientists baffled, standards, headlines anytime there's something like this. There is a discrepancy. There is something unexpected. Something unexpected is always fun because this is now something to figure out. But there are several caveats that we need to do here. Thank you for joining, David. It's always nice to have you around when you join. If the two experiments are outside of each other's error range, that tells me the error calculations are more suspicious than the standard model. Thank you for that comment, Paul, because that is exactly what I want to get to now. So there are a couple of issues with this new measurement. The first one that I've heard from the theorists, so from people working on these standard model calculations, is that this uncertainty that we give in the standard model prediction is a bit too tight, that we actually really don't have that level of precision in our calculation. Because as I mentioned, this calculation depends on several other observations that we have measured. So people on the theoretical side have said that this standard model prediction should actually have bigger error bars than what the CDF people are comparing to. Another big caveat or big issue that we need to address with this is how it compares to other experiments. So I'm going to bring up this other image here, which is also from the paper. Now what you can see here is the measurement done by different collaborations. Oh, thank you for the nice comments, Harry. I'm glad the explanation is coming across properly. So what you can see here is the measurement. So in the bottom axis, on the horizontal axis, again, we have the measurement or the value of the W boson mass, the mass of the W boson. Now each line here corresponds to a different experiment. First of all, you see this grey band, this grey vertical band. This is the standard model prediction. Now if we look at the top one, this one D01, this was an experiment that measured the W mass many years ago. The red point is the central value and the lines around it give you the uncertainty. This means that the measurement should be somewhere in that range. You can see that D01 was a bit off of the standard model but had very big error bars. Cdf1, which was the first version of the measurement from 10 years ago from the Tevatron team, was slightly higher than the standard model but still consistent with the red bars. And then if you go down, you can see that all of these numbers are kind of around the standard model value. Now, the most precise one we had until Thursday was from the ATLAS collaboration, which is part of the Large Hadron Collider experiment. Now, ATLAS is one of the 4 detectors at the Large Hadron Collider. And you can see here, second from bottom, that Atlas was really, 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 really close to the standard model value, basically on top of the standard model value with very small error bars. This new CDF one, the bottom one in red, is the new result. You can see that it is substantially higher than the standard model value with very small error bars. So the big question here is, why is CDF2 different from CDF1? Why is it different from Atlas? Why is it different from all of the other experiments that have come before it? This is something that nobody has an answer to. It could be that CDF2 is wrong, it could be that all the others are wrong, it could be that everyone is right. This is something that they were asked in the press release and basically gave a hand-wavy answer of who knows. What we can say is that CDF has spent 10 years refining their measurement, 10 years looking for mistakes, improving, doing everything they can. And they did a blinded analysis, so they did not know what number they were going to pull out. There's a thing we do often of blinding it, where you basically put in fake numbers and you go through the whole pipeline, and then right at the end you do the unblinding, where you add in the real numbers, and at that point you see the result. And the reason for doing this is to make sure that scientists don't put their own opinions of what the numbers should be. So you do it in this blinded way, where you go through the analysis, you do everything you can, and then right at the end it's revealed. And this is what CDF did. It was a complete blind analysis until 2 years ago when they unblinded it, and everyone in the experiment was like, okay. They unblinded it, they spent 2 years looking for any problems, they didn't find any. So what do we have? We have a new measurement of the W boson, which is 7 sigma away from the standard model value. 2 caveats. We do not know just how precise the standard model calculation is and how much we can trust these error bars. Caveat number 2, CDF, these results, this new result, is intention or is different to results we've found before. Does this mean we need to check out the standard model of particle physics? No. We have found something interesting, we have found something unexpected. This is the point where we need to go and poke it with a stick to figure out what is going on. It could be a hint of new physics. If it's new physics, then we need to explain why CDF measured one thing and Atlas measured another. I saw one theorist make the comment of, or one physicist make the comment of, the mass of the W boson should be the same in Europe and in America because CDF is in the US and Atlas is in Europe. There's no reason why these experiments should produce different results, but they have. Now, of course, if we have one experiment that agrees with theory and one that doesn't, which one do you trust? Both of them, neither of them. The answer is to do more experiments. We need someone else to come along and reproduce this result. We need a next collider. The Large Hadron Collider is going to increase its energy very soon. It's going to measure more W bosons. We can expect another measurement there. We need another collider to come along and measure this. So this is very exciting. It is really interesting. I can tell you this news came out like Thursday evening my time, and I stayed up late reading all of the articles about it, looking into it, because it is exciting. It is not the point where we need to chuck out the standard model. It is not changing the whole future of particle physics like some news articles would have you believe. It is interesting, it is unexpected, and now we need to go figure out what is happening. We have a measurement that is different from the prediction. It is also different from previous measurements. This is fun, this is exciting. So, I know I rambled a lot. There was a lot of theory I put in today because I wanted really to build up this result. I hope the introduction to the particle physics model helped you appreciate why this is a big deal. The standard model of particle physics is one of the most well-tested theories we have, but we know it's not perfect. We know there are cracks. And now we found another crack, and this is where we're supposed to go and peer through it and see what is happening. There was the comment here, is gravity skewing the results? We don't know how to put gravity in with everything, so probably not. Gravity shouldn't be affecting things that are so tiny, so probably not. If a collider was built in space, would collisions result be different? I don't think so, because the only big difference you would have is the noise, the background noise, like muons coming from space going through your detector, but you also have that on Earth. So I'm not sure what really would change going to space other than, you get free cooling, but it's a bit harder to build something in space. There's an excellent comment by Paul here, and thank you to everyone saying you appreciated the explanation. That is always good to hear. And thank you for the love celebration, and I do appreciate the love celebrations. Z and W bosons do have mass. They interact with the Higgs field, they do have mass. Anything that has mass cannot travel at the speed of light. The only things that can travel at the speed of light in a vacuum are things that have no mass. Photons and gluons and the Higgs field, no, photons and gluons all travel at the speed of light. The Higgs boson has mass, so it does not move at the speed of light. But everything that has mass cannot travel at the speed of light. If it has no mass, it can travel at the speed of light. This is really cool in the case of electrons, because we used to think that electrons traveled at the speed of light, and then we figured out that, neutrinos, not electrons. Electrons have mass, they do not travel at the speed of light. We used to think that neutrinos traveled at the speed of light, then we learned that neutrinos have mass, and therefore they do not travel at the speed of light. And thank you, James, for the Heart Bomb Award. If it is heavier, does that mean the weak force propagates more slowly than predicted? Yes. That is a very, very interesting conclusion here. If it is very slightly heavier, it means the bosons must travel very, 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 very slightly slow. I think the change would be negligible, but it is something that we can say here, that the bosons might travel slightly slower because of the increased mass. That is also true. Of course, you can just accelerate them and give them a kick, and then you get them back up to the speed. So we know that the W boson has mass. We have a prediction for this. We now have a measurement that differs from the prediction. We have previous experiments that agree with the prediction. It's interesting. There's a crack. Now it's time to peer through the crack and see what we'll find. So I don't agree with the headlines of physics is broken, obviously. Science is baffled. I would say more intrigued than baffled. But it is interesting, because any time there's a mismatch, this is where there's a chance of moving forward. This is where the science can progress. So it's interesting. I'm really looking forward to seeing what we're going to do with this measurement. And I say we, not me personally. This, as you might have noticed by some of my hand-wavy answers, this is not my topic. This is particle physics. This is not really cosmology. But it is the building blocks of the universe, so how could I not talk about this today? It is exciting. It is very interesting. It is nice to see that there are cool things happening. And I am sure over the next week there will be hundreds of papers trying to explain this theoretically. Hundreds of beyond the standard model theories, hypotheses, trying to explain this. We're going to have hundreds of papers doing this. But what we really need is another experiment to come and verify this result. And that's exciting. This is an exciting time. So it's definitely an interesting result. It's definitely something getting hyped up, to be hyped up about. But it is a bit overhyped in the media. And it always annoys me, because this result is really cool by itself. We don't need the sensationalist headline of physics broken, because it's already a cool result. We don't need that. And it dilutes the message, in my opinion. But that's a rant that you've all heard me go on many times. But yeah, it's cool. To everyone who tagged me in Twitter and in stories about this, thank you. I love knowing that you see some random physics story and your first thought is, I'll ask Diana to explain this. I love that, so thank you. If you see any random physics story, please do feel free to tag me or DM me. Or someone even emailed me like, can you explain this? Yes, absolutely I will, because it's a cool topic. We need another experiment with small error bars and another different number. Yeah, if we get another experiment now that measures a smaller mass, that would be fun. Maybe the W mass boson the mass changes depending on the day. That would be utter chaos. That would be throw out physics and start again. But it's definitely fun. It's exciting, and it's a very interesting time. And I would have liked to get a particle physicist to come on the show to explain this a bit better than I would have done. But this result came out on Thursday. It's a bit short, Thursday night, so it was a bit short notice to get a guest on. But I knew I had to cover this topic today, so I hope the explanations were clear enough. Another experiment with different tech, which is replication of this one. Different tech would be nice. I mean, this Teflon experiment was operational over 10 years ago, so we do have good technology. But something that just remeasures it, ideally in a different way, this would be cool. This would be ideal. Now, of course, good luck getting a new experiment funded. But there are hopes in the future. There are already plans for future colliders that could measure this. I think the sensationalist headline is because they don't have you to explain it rationally. Thank you for that nice comment. Yeah, it's clickbaity. I was almost put a title today of "Is Physics Broken?" and I thought, no, I'm not going to do the clickbaity title. It doesn't need it. So yeah, thank you everyone for following along with the explanation. It's always fun to talk about these things. I hope I've convinced you that it's fun, it's interesting, and it's worth paying attention to. And I know, James, at 6 minutes past the stream, you said 60 minutes start now, so I think I've kept to the 60 minutes you requested. I went 6 minutes overtime specifically for that. Next Sunday is Easter Sunday. I will not be doing a stream. I will be spending time with my extended family. So I will not be online next Sunday. I should be online 2 weeks from now, so that's Sunday, 24th of April. I don't yet have a topic planned or a guest. I have 2 weeks to figure it out. But don't look for me next Sunday. I will be taking Easter Sunday off. But I will be back 2 weeks from now. And then I'll have potentially a cool announcement about an in-person science outreach event happening in Munich in a month for anybody in the Munich area. More details to come. Not going to reveal anything until that's set in stone, but pretty excited about that. We'll share details soon. Okay, thank you everyone for joining. This has been great fun. It's always great to have you here asking cool questions and tough questions. Always great fun. I hope to see you next Sunday, same time as today. And I hope in the meantime you all stay safe and take care of each other.